Huh. Didn't detect another display. Hmm. Well, what's going on? Oh dear. Well, crap. There. There. Okay. Folks at home, somebody say that you can hear me.
We can hear you.
Okay, great. Thanks. All right. Somebody changed the display settings for reasons known only to them. I have no idea what was going on, but let's get going. Okay, so we've got yet more things to give back. I am posting the grades for the second exam or for the third exam as soon as possible. I would have had it done already, but things got a little strange on Monday and Tuesday. So we will get that up as soon as possible. The good news is that 5 people got 100% on that exam, and it's the highest average by far that we've had so far. It's higher by 20 points than the second exam was. So good news for some people. Some people still didn't do that well, though. So we'll be posting that soon. Now, the fourth exam is on the Monday before the Thanksgiving break. You really need to take that exam if you're going to. If you miss that exam, you're just going to have to drop it because I won't give a makeup after Thanksgiving. That is just too late given when the drop date is. So I hope you had a chance to look at the FoodWeb's presentation on schedule. It is an important thing, and I'm hoping that it won't mess you up too bad having to do that, but I'm certainly open to questions about it anytime. And what we'll do now is do succession. All right, and succession really requires us to have talked a little bit about FoodWebs and about how communities are organized. So we'll do a few things today. We'll talk about just what we conceive of as succession. We'll talk about primary versus secondary succession and the characteristics of successional species. This will be very familiar to you if you recall R&K selection. We'll talk about the fact that succession is a useful idea, but it doesn't always apply to every situation. And we'll show you a situation in which it's really sort of impossible to apply the classic concept of succession, although you can clearly see that succession is occurring. And then we'll spend a lot of time trying to help you understand the three different mechanisms of succession, because these are very confusing to most people. And one of them is the one that you mostly find in primary succession, and the other two are mechanisms that generally work in secondary succession. It requires some thought, some careful thought about what you expect to see, to know if you're looking at one of these three mechanisms. But once you sort of see what you need to look for, I think it gets easier. So I'm going to spend some time on it. I'm going to try some things that we hadn't tried in semesters past. Okay, so succession is the temporal change in the species composition of a biological community. And you can see why we want to talk about food webs first, because food webs is the organization of the community at any given time. So whether you have X or Y trophic levels and how those species interact. Well, those things don't stay constant over time. They change as time goes on. So there's a succession of species that inhabit a particular community over time. And because plants don't run away from us, we usually talk about succession in the context of plant communities. But it's important to realize that animal communities follow exactly the same rules. You see a succession of species taking over and some disappearing in animal communities as well. So primary succession is where we first got this idea. The whole idea of succession comes from observing what we call primary succession. It's succession that occurs in an area that has no pre-existing community. So what would be an example of that? Well, a sandbar produced by a river that initially has no plants growing on it. And then suddenly some grasses spring up and then trees. So that's where this kind of comes from. The most famous example of primary succession is glaciers receding in Alaska, which we'll talk about a bit. But in Katmai Bay, the glaciers receding from the coast exposed bare rock. And it took, some hundreds of years for the local mature forest to develop on that bare rock. And during that time, there's a whole succession of species. So that's primary succession. Secondary succession occurs when there is a disturbance to a community. So elements of the pre-existing community still are present. So a fire may destroy some plants, but leave the seed bank untouched. A tree fall in a forest may take down a large number of plants, but it's not like the entire forest is destroyed. There are plenty of plants there to recolonize that disturbed area. So secondary succession has elements of a community already present. Primary succession has no pre-existing community. And in fact, conditions may be extremely harsh for the establishment of a community. So that's the fundamental distinction here. Now, a couple of more terms. SERE, or S-E-R-E, is a stage in a successional sequence. So we can have early successional seers, we can have middle seers. It's a snapshot in time of a moving picture. So you think of it as a scene from a movie. A seer is not in itself a thing, just as a community has no objective existence except to the investigator, or a population is defined for the purposes of an investigation. We generally simply distinguish early, middle, and late successional species groups, and without trying to make too much out of it. You can get some late successional species early in succession, especially in secondary succession. So don't, SEER is a general term for stage in succession, is a term of convenience. It's not meant to be a hard definition. Okay, the climax community, however, does have a particular definition. It's the final stage in a successional sequence, and it's a community that replaces itself indefinitely. Okay, the only thing that can overturn a climax community is some kind of disturbance. So the concept of succession then is that there's this development of a community over time to maturity, and the mature community is the climax community. And I think you can see why this fit in really well with the idea from the early 20th century that communities were kind of like organisms, because not only did they have their species and the species played particular roles, just like organs within an individual, but they changed it over time, and they went from a immature stage to a mature stage or adult stage. That term was actually even used, adult community, which of course means something else today entirely. But the climax community then is what the original conception of succession ended with. And we'll see that, well, okay, sometimes you can maybe define a climax community, other times maybe not. So here's some examples of succession. So this is the Michigan Dunes National Park. And what you see is that the Great Lakes are receding. The level of the lake is dropping. And so as that happens, you're uncovering bare sand that had no terrestrial community. And on the top left here, you see more or less bare sand exposed by the retreating water, and you see these little wispy grasses that have colonized it. Okay, well, this area of the Midwest is characterized by oak forests. Where are the oak trees? Well, there aren't any. And there's a good reason for that. We'll go into that in a moment when we talk about primary succession. But this is what primary succession looks like. So you get these wispy annual grasses, then you get bunch grasses that stabilize the sand and build up organic matter, because there's no carbon, there's no nitrogen in this sandy soil until the plants start growing and dying and adding that to the soil. Here you see the third stage, which is that the bunch grass stage is overtaken by shrubs and small trees as soon as there's enough organic matter in the soil to support them. And then here's your climax forest, long-lived oak trees. And this sequence takes roughly 150 years. So here's a second primary successional sequence for us. This is ponds in Canada filling in with sediment and turning from aquatic environments to a climax spruce fir forest, or spruce hemlock forest in this case. So here you see the open water and you see the plants at the edge of the water. As these plants die, they add organic matter to the pond, more or less filling it in gradually. Okay, and here's a pond that's way advanced in the process of filling in. And what you can see is that very little open water is left, and you've got all this marshy stuff where soil is building. And that's where these grasses and herbs are coming in. And then around the edges, you can see these darker shrubs as the water in the soil is reduced and the organic matter is increased. And then in the background, you see the spruce hemlock forest. And this is the spruce hemlocks coming in at the end of succession, finally closing out this aquatic habitat. Okay, so there was no terrestrial community there. There's no seed bank for these terrestrial plants. They have to colonize de novo, as we say. Okay, here is one of the most famous studies of secondary succession, which is an abandoned field in Poland. This was a mid-20th century thing that that happened, and what we are seeing here at the top left is an abandoned field, roughly the year after it was abandoned, and you see that there's forests surrounding it. So this is definitely secondary succession. Here is about 5 years later, and you see that a lot of shrubs, well, not a lot of annuals have grown up very densely, and even some small shrubs back here. About 15 years after that, you see the first woody plants really starting to come in, okay, and they're starting to shade out some of the small plants underneath them. At 50 years, 30 years rather, this is 30 years, you see that it's beginning to look like a forest, and the trees have become well established, although they are small trees. And there are species that tolerate high light levels and require high light levels to germinate. However, in the understory, there are some seedlings of trees that are shade tolerant. And here you can see these trees now growing up, overtopping the early trees and shading them out. And then about 150 to 200 years later, you see what is almost indistinguishable from an unaltered primary forest with shade tolerant trees and a relatively open understory because of all the dense shade. Now, secondary succession is extremely common everywhere on Earth. I used to work in Panama on Barrow, Colorado Island in the tropical rainforest, and it was an amazing place. You had trees that were, as big across as both of these tables put together, and no hint that this was anything other than a primeval tropical forest. But in fact, 500 years previously, it was a cornfield. And what happened was Balboa kind of stopped off on his way to the Pacific and conferred some diseases on the local indigenous population, killed them all off. They abandoned their fields. And then you got the hilltop forest that is now Barrow, Colorado Island. That is a laboratory for tropical biology the world over. So secondary succession here. Now, we see succession in many, many, many contexts. Here is a hillside in New Hampshire where we see waves of succession caused by blowdowns. So you get one of these windstorms coming up out of the Atlantic Ocean, moving north in New England, and the southern slopes of the hills are exposed to these really high winds. Gee, we wouldn't know anything about that here, would we? But if they succeed in blowing down trees, they open these gaps. Okay, and so what you see here is the leading edge of the gap. These trees right here are the most exposed to the wind. They're old trees, but they have no protection from the wind. And so the next windstorm that comes through is going to blow them down and advance this front, this wave up the hillside. What you see immediately behind them is this open space. This is what is left when all the trees blow down and the grasses colonize the open area. And then down a little further, you can see that it starts to get greener. Well, these are shrubs that are starting to take over from the grasses. And then further down the hill, you would see mature trees again. But these trees are not going to survive. They're going to be blown down, and this front is going to gradually work its way up the hill with grasses following behind, and then shrubs, and then finally trees filling in 100 to 200 years later. So we see succession in both human and natural situations. Now, very important, we just said that things like grasses are the early ones and herbs are the early plants to make it in a successional sequence, and trees are the ones that come late. So that tells you right there should be some characteristics of organisms that predict whether they will come early or late. And so here are the general characteristics of plants that are regarded as early successional and late successional. And this should look shockingly familiar to you. The early successional plants produce many seeds. They are small. They are easily dispersed long distances by wind or by animal dispersal. Gosh, let's see, many small seeds. They tend to survive well in the soil. The root to shoot ratio is low. That's because they're producing above ground parts as fast as possible to reproduce before bigger plants get there and shade them out and kill them. So their growth rate is rapid and their mature size is small and they can't tolerate shade. What does that sound like? Many small offspring, early reproduction, small body size. It sounds like what? From life history theory. R selection. These are R selected species. They're selected for early reproduction. Get it while you can. They're lousy competitors. And the way that a lousy competitor maximizes its fitness is to produce many small offspring, hoping that some of them will get through to adulthood. For the late successional species, they produce many fewer seeds per kilogram of mass. They produce large seeds, and they produce seeds that have different characteristics. They either fall under the tree or are dispersed by animals, but they don't have long viability in the soil. Although this is you'll see that this is we'll have to modify this a little bit. But here's what to focus on: root to shoot ratio. Lots of roots compared to the above ground biomass. So they're setting themselves up for the long term. They are not trying to bolt up and reproduce quickly. They're trying to set themselves in the soil to endure a siege that may last 200 years. They grow slowly because they grow large, and they are highly shade tolerant. So let's think about that then. Few offspring, large body size, slow growth. Those are K-selected species. So it makes perfect sense that succession should have a logical sequence of traits associated with it. K-selected species tend to be the dominant species because they're good competitors. And what do we know about K-selected species? They're the good competitors. They get to their carrying capacity and compete. R-selected species, excuse me, are poor competitors, and they try to bomb the environment with as many offspring as possible in the hope that a few of them get through and reproduce. So we can tell that even among the later successional species, there's a successional sequence, and that has to do with shade tolerance. So the early successional trees, which are kind of mid-level, kind of mid-successional species at best, have different characteristics than the late successional dominant species that would form the climax community. So here are the early trees that first colonize as soon as herbs and shrubs provide them the opportunity. And look, they have relatively small seeds. And they don't survive well in the shade. They need sun. So even among the trees, there's a gradient. Really early successional species like grasses and herbs require sun. When you compare the trees at different stages of succession, the early successional trees require more sun than the late successional trees. So these trees are not as good at competing for light as the ones that come later. And you see that as seed size increases, so does shade tolerance. So the mortality is very low here for the largest seeded trees. Now, this is not quite the same thing as viability in the soil. These things have to germinate. Once they germinate, they can tolerate low light levels. So this graph refers to what happens after germination, after they produce their first leaves. So the larger seeded species are more shade tolerant. They can wait it out until they get an opening to exploit. And it may take them 100 or 200 years to find that opening and finally reach the canopy, but that's their strategy. These guys, despite the fact that they are trees and relatively large as plants go, are still kind of more are selected because they mature quicker than the climax trees, and they reproduce faster, they produce more seeds, and they produce smaller seeds that require high light levels. So once you get a dense canopy, all these things disappear. And only the most shade tolerant trees are left. So there is a sequence of traits that suits organisms for early, middle, or late successional status. Okay, and a really important thing to understand when you look at a community is you need to look to predict the future of the community. You need to look at who's reproducing. So as it turns out, if you go back to these guys, these birch, sumac, and tulip trees, they will be the canopy at some point, right? They will be the dominant trees in middle successional stages. But the question is, will they stay the dominant trees? Well, you can tell by looking at what young trees have germinated underneath them. And that's what this is all about. So in this community, here are the saplings that you find under the canopy of these trees. Now, at the moment, at a snapshot in time, you'd think that this is an oak forest because you have these white oaks and black oaks. But actually, under the canopy, look how many oak seedlings are germinating here. None. And don't be confused by the fact that we had oaks being shade tolerant in the previous slide. There are like 100 species of oaks in North America. Some are way more shade tolerant than others. And that slide referred to a different kind of oak. Okay, but nobody's germinating here. So there will be no oak trees 100 years from now. On the other hand, what you're going to see mostly is beeches and maples, because those are the young plants that have germinated under this canopy. So regardless of what this looks like now, this is what it will look like in the future. This will be the climax species. All right, now let's, we've kind of set out a situation in which we have this concept that communities go through this succession And they start with certain species with certain traits. And as time goes on, more and more competitive species crowd out the early ones until you reach a climax community. Well, okay, that doesn't work in every case. And here's an example. This is why we kind of, use our judgment a lot in thinking about ecology. Oops. But here is a system in England on the heath, which is the kind of barren Hound of the Baskerville setting that you might find in central England, that does not have a clear successional sequence. In fact, it has what we call circular succession. So the heath is disturbed by waves of disturbance that are generated by wind, okay? And as plants are battered by the wind, they tend to die, okay? And they open up space. So they open up bare areas. Well, what happens then? Well, the plants that are dying are called Calluna. Okay, and that's these guys right here, these tall, light green things that are diagrammed here. So these Calluna shrubs are the ones that are battered by the wind and eventually die, opening up bare space. But sandberry is a shorter lived, easier dispersed plant that colonizes those open spaces. So down here at the bottom, you can see this sandberry is advancing into this open space. However, Calluna, the thing that originally died, outcompetes sandberry because it's taller, so it shades it out. So what you get is a sequence of bare ground colonized by sandberry, shaded out by Calluna, killed by the wind, opening bare ground, colonized by sandberry all over again. So, hey, we said that a climax community was one that replaced itself. And there's no climax community here. So we want to be careful about applying these ideas uncritically. They can help us understand ecological phenomena, but they are not laws of nature. Sometimes you'll get something that you can call a climax community, and everybody will agree that, yeah, that's pretty much a self-sustaining, self-replacing set of species. Other times, like here on the Calluna Heath, you don't get any self-sustaining community. No community replaces itself. Instead, you get this circular succession. So that's the kind of bare bones of our ideas about succession. Now, I want to switch gears and talk about mechanisms of succession. There are three, and they can be really hard to get a grip on. So I'm going to try something. I'm going to try to show you some numbers to help, maybe help you get a handle on it. At worst, it will just confuse you more, but I'm hoping that it will not. So let's go through the three. First, there's facilitation. In facilitation succession, each species changes the environment in ways that permit other species to colonize. And succession proceeds as available niches become change over time. So think about the dunes that are exposed on the shore of Lake Michigan. What's in the soil? Not much. There is no nutritional niche that could support a tree. But there is just enough moisture to support these scant little grasses that are the first stage in succession. As they die, they add nitrogen and carbon to the soil, building the soil richness and adding a dimension to the soil that allows other species with more demanding niche requirements to colonize. They might need more water. They might need more nutrients. Well, those are supplied by those initial grasses. And then when the bunch grasses die, they will further enrich the soil, making it more suitable for things like shrubs. Well, okay, so shrubs and trees cannot colonize bare soil. They cannot, their niches are not present. So the early successional stages create new niches. And unfortunately for them, the plants that inhabit those new niches tend to be competitively superior and cause the extinction of the earlier stages. So this is what we find in primary succession. The other two mechanisms are what we find in secondary succession when there is a pre-existing community that has not been totally destroyed by some disturbance. The first is inhibition. And in inhibition, each species is pretty good at holding space. They're about equally competitive. And they prevent any other species from taking their space until they die. When they die, then a spot opens up and it's up for grabs. Okay, so the thing that drives succession in inhibition is the lifespan of the plants. Plants that have short lifespans die more frequently and they turn their space over more frequently. And if a longer lived plant can grab that space, it won't turn it over and it will come to dominate the community. So inhibition succession is driven by differences in lifespan. All these species are more or less competitively equal. Okay, and the last one is tolerance, in which some species are better at tolerating competition than others. So species compete for resources and some are better at it than others. All the niches are present, but some species are good at competing, others are not. The ones that are not good at competing die off, leaving only the ones that are better at competing. So in facilitation, it's driven by the absence of niches and the creation of new niches. In inhibition, it's driven by differences in lifespan. Everybody's equally good at competing. In tolerance, it's driven by competition. Some are much better at competing than others. So that's a brief summary. I'm going to try to go through these and give you examples of where we see them and hopefully show you what you could expect in terms of different stages of succession and how they could grab open space or how they would succeed each other. So first in facilitation, here's a couple of examples. Here's a glacier that's receding and leaving bare rocks. Well, ain't nothing going to grow in those bare rocks except lichens maybe. And they're going to break down the rocks into soil. And there are literally no niches for plants like trees until these early successional species create them. Here's a volcano, and you can see the lava flow that has destroyed the forest. Okay, there's no pre-existing community left in these areas of lava flows. And they will have to undergo a process of soil formation and enrichment because the niches to support many of the late successional species simply aren't present. All right, so let's try to use some numbers to illustrate what that might look like. So here, if we have state at time t and state at the next time period, we have open and we have early successional, middle successional, and late successional. In facilitation, there are no niches available for the middle and late successional species. So the only thing available is for open space to be colonized by the earliest successional species. And notice I didn't make it 100% because it's not realistic to make this 100%. But most of the open space is going to go to the early successional species because they're the only ones that can tolerate it. There are just no niches for anybody else. But once you get the early successional species, they're creating niches for the next group, right? So if open space is colonized by these plants, what happens to the space that these guys occupy when they die? Well, some of it will turn over back to open space. They'll keep some of it, but mostly, look what's going to happen. The new niches that become available favor later successional species. And then these guys will create new niches that favor this climax community here. So when the mid-successional species die, well, some of their space might turn over into open space. But look, the early successional species probably aren't going to get any of it. It's mostly all going to go to the climax community. And then the climax community here replaces itself, remember? So you got a pattern here. You have a pattern of who colonizes open space and who succeeds who. So open space is colonized only by early successional species, really, because that's the only ones that can find niches for themselves. But they change the available niches to favor the next set of species. So you get open space colonized by the early successional areas here go to mid-successional plants, and mid-successional plants go to the climax community. And there are no niches left for these guys. Okay, we're going to try to use this to help you visualize what's going on. Okay, so there are two key things here then. Open space is grabbed by the early successional group. And I have A here, it might be one species, but it might be like 30 different species that come in early in succession. The early successional species are the only ones that can grab this open space because that's the only niches that are present. And then community A turns over and goes to community B because it's created the niches for the mid-successional species. And then community B has created the niches for the late successional species. So it's a very orderly process. Open space goes to early successional, pretty much only. Early successional goes to mid-successional because they haven't created the niches for late successional species yet. And then the mid-successional species create those niches and they go to the climax community. And then the climax community replaces itself. So this is the kind of classic idea of succession that was first elaborated in the early 20th century. Now in inhibition, everybody's equally good at competing. Where would we find that? Well, when all of the plants have the same growth form, like on a prairie. So prairie succession is often inhibition succession. Each plant keeps its space until it dies. And the ones that die quicker turn their space over and go extinct. All right, so remember, this is secondary succession. So there is a pre-existing community. All the niches are present, and that means that early, middle, and late successional species can all share the open space. Their niches are already present. Okay, and notice that the early successional species tend to keep their space. They don't turn it over all that much. The middle successional species keep their space, In fact, they keep it better because they live longer. And the climax community more or less just keeps the space. Okay, so these numbers increase. Okay, so the highest number in each row is staying in your own state. Like if you are an early successional plant, the most likely thing that's going to happen a year later is that you'll still be an early successional plant in that stage. This is not at all like facilitation. In facilitation, the early successional community would turn over most of its space immediately to the mid-successional community. So these numbers are a different pattern than in facilitation. So two things. First off, everybody gets a share of the open space. That's not like facilitation. And the most likely thing to happen is that you keep your space. And the shorter lived guys don't keep their space quite as long as the longer lived guys. So succession is driven by lifespan, right? Everybody gets open space. Eventually though, because you live different numbers of years, the ones that live the longest in the climax community are the ones that are left over. And the shorter lived ones have lost all their space. And so then they are another good climax community. The last one is tolerance. Okay, and in tolerance, remember we have good competitors and bad competitors, not like inhibition at all. Okay, and that's what we have in forests, right? Because we have little herbs and we have tall trees that cast dense shade. Okay, what these plants are competing for mostly is light. Okay, so in secondary succession in a forest, you'll get some plants of each stage getting a share of the open space because the niches are there. But the early successional ones have so many seeds that they get most of it. These guys have fewer seeds and bigger ones, and these guys have the fewest seeds and the biggest seeds. So they all get it, but the early successional species get more of it. And then look what happens. Because the niches are already there, it's really even what happens to each of these communities. The early community gives up its space to B and to C because the niches are there, and it doesn't matter who's out competing the early successional community. Both the mid and late successional communities can outcompete them, so they grab this space. The early successional community basically dies out, and the mid successional community gives up its space gradually to the climax community here. So they all get some open space, but there's a real sharp gradient. And notice the numbers here on the diagonal. These guys are really bad at keeping their space. These are better, but the climax species are the best. So open space gets colonized by everybody, but more so by the early successional species. Okay, and there's a steady progression in the ability of these species to hold their space. These are bad competitors, medium competitors, really good competitors. Okay, so this is how it works then. Most of the open space goes to community A, the early successional guys, but then it goes pretty equally to mid and late successional species. And the best competitors in community C, the climax community, they're the ones that take over, and everybody else is sort of left in the dust. So there are different patterns that you expect. In primary succession, in facilitation, you expect only the early successional species to be there initially, because that's the only niches that are present. In inhibition, you expect everybody to be pretty good at competing. And turnover occurs because plants live different lengths of life. In tolerance here, the competitive ability, the ability to hold your space, A staying A, B staying B, increases because these guys are way more competitively dominant than these guys, and they're more competitively dominant than these guys. The numbers are very even in inhibition. So the important things to remember then are who gets the open space? And do you replace yourself? Or is there a gradual change from the community that you dominate to a community that crowds you out? And this requires a little bit of practice. I'll put a practice problem up there. You know, there's only so much we could do with numbers like this and really simple patterns, but you know, you'll get a chance to try to work through it and see the logic for yourself. I've also got to get that Shannon Weaver problem set up for you, but I'll do that today. So unless we have questions here in class or at home, I will see some of you either at the cemetery at about 1:15 or 1:20, or if you have no idea where you're going, come to Bio 216 and I'll help you figure out where you're going and we'll drive together. Okay. That's it. What's that? Yes, I was hoping to do that today, but that didn't happen.